Okay, so welcome back to this second video in which we are discussing endothelium-dependent hyperpolarization. Okay, so we are discussing the experiment that Bolton et al. Did. So, they were stimulating endothelial cells with either acetylcholine or also carbachol. I think they were actually using carbachol, and we'll discuss what the difference between those two is in a moment. So this is carbachol. In fact, we'll discuss what the difference between the two is now. So carbachol is pretty much identical to acetylcholine, and indeed it can act on nearly all acetylcholine receptors. In fact, it can act on all acetylcholine receptors, exactly like acetylcholine. So let me show you how similar they are. So, if we start with carbachol, which seems a bit of an odd way to do it, but I drew the structure of carbachol first. So if this is carbachol here, so basically what you have is this group here. As we'll see, in fact, let's start with acetylcholine. We'll start with acetylcholine. It's the more sensible one to do first. So acetylcholine, the reason it's called acetylcholine is because you have an acetyl group esterified onto a choline molecule. So here is your acetyl group, and then you've esterified it with choline. So here's your choline group down here. So choline has an alcohol group, basically. So here is the alcohol group of choline that's been esterified with the carboxylic acid group of acetic acid. Okay, and then the rest of choline is you have an ethyl group, like so, and then a nitrogen on the end, which has 3 methyl groups coming off it, like so, 1, 2, 3, and then overall has a positive charge. So choline, if you can imagine this structure that we've got here, but just with a hydrogen on the end of that oxygen to make an alcohol group, rather than having this acetyl group stuck on the end, that would be choline. So this is the choline portion here, and this is the acetyl group up here. Okay, so let me highlight these in. So the acetyl group is this portion here. It's basically acetic acid with its alcohol group removed from the carboxyl group. So it's the acyl group of acetic acid. And then choline is this portion down here, which we'll have in turquoise. Okay? Now, carbachol is basically exactly the same thing as acetylcholine, except instead of a methyl group attached to this ester link here, instead you have an amino group, as in here. So, here comes the rest of the choline molecule, which will remain exactly the same as it was in acetylcholine. So here's the ethyl group, here's the nitrogen, and the nitrogen will have these 3 methyl groups coming off it, like so, 1, 2, 3. So this is the structure of the molecule carbachol. Okay, and basically, as you can see, it's almost identical to acetylcholine, and it can act, it's an agonist for all of the acetylcholine receptors, both the nicotinic acetylcholine receptors and the muscarinic acetylcholine receptors. So often it is used to stimulate these receptors. So it will stimulate the M3 receptors, which are on the endothelial cells. And what Bolton et al. Noticed is that when you stimulated these M3 receptors on the endothelial cells, what you got was a hyperpolarization of the electrical potential difference across the membrane of the smooth muscle cell. And by the way, I've looked this up. Negative 85 is not the electrical potential difference you have across smooth muscle cell membranes. Instead, you have an electrical potential difference of around negative 60 millivolts. This is more like what you have in cardiac muscle cells, so not smooth muscle cells. Smooth muscle cells are have a much lower electrical potential difference across their membrane. Right, so what this means, however, this electrical potential difference of negative 60 millivolts, is that the electrical potential of the intracellular compartment here is 60 millivolts lower than the electrical potential of the extracellular compartment, which means that when we put this in and subtract off the electrical potential of the extracellular compartment, we're going to get negative 60, basically. Okay, so if you moved from here to here, you'd go down by 60 millivolts. Right. So, what you see upon stimulating the endothelial cells with carbachol or acetylcholine is this becomes hyperpolarized. So maybe it goes to negative 65 millivolts, or maybe even lower. Okay, that's what it means to become hyperpolarized. Hyper means too much. Polarized means different across the two sides. So it's become too much different. Hyperpolarized. Okay, and this is the first time that endothelium-dependent hyperpolarization was observed. It's a hyperpolarization that occurs across the membrane of the smooth muscle cells in response to stimulation of the endothelial cells, or of the endothelium. So it's an endothelium-dependent hyperpolarization. Moreover, Bolton et al. Didn't stop there. What they did is they removed the endothelial cells from this mesenteric artery here. So they removed the endothelial cells. And then, if you stimulate with acetylcholine or carbachol then, instead you no longer get the hyperpolarization, and instead, across the membrane of these endothelial cells, instead you get a depolarization. So if you remove the endothelium, then you get the exact opposite effect. So what happens now is, instead of the acetylcholine or the carbachol acting on the M3 receptors on the endothelium, instead they act on the M3 receptors in the smooth muscle cells, and then cause the release of calcium from the intracellular stores, which causes depolarization of the cell membrane. So remove endothelial cells, and what you get is depolarization rather than hyperpolarization. So when you stimulate the smooth muscle cells directly, because you've got removed the endothelium, and you can do this merely by sort of scraping the artery, basically. Scrape the artery wall, and then you remove all the endothelial cells. And if you then stimulate this scraped artery, where you've scraped off all the endothelial cells, you will then get a depolarization of the electrical potential difference across the membrane of the smooth muscle cells. So this really is an endothelial-dependent hyperpolarization. Okay, so let's look at another experiment that was done. So initially, what they thought was, well, maybe this is nitric oxide again, because what we know so far is that when we stimulate these M3 receptors, either with acetylcholine or carbachol, then what it's going to cause is it's going to cause these endothelial cells to start producing nitric oxide. We know this very, very well. We've spent many videos talking about nitric oxide. So you're going to send nitric oxide, NO, to the smooth muscle cells, and we know what this does. It activates the soluble guanylate cyclase within the smooth muscle cells to produce cyclic GMP, and that produces relaxation of the smooth muscle cells. Well, maybe the nitric oxide also is responsible for this hyperpolarization. Maybe it's causing the hyperpolarization. So what we then did is some experiments that show that that can't be done. Well, that can't be true. Okay, so this was done by Chen et al. In 1988. So Chen et al. Came next. They wanted to investigate whether this was nitric oxide doing this. Okay, so in 1988, what they did is they did pretty much the exact same experiment. Okay, and they took an artery and they stimulated the endothelial cells with acetylcholine or carbachol, and they got this hyperpolarization. And then what they did then was they used pharmacological agents which would block nitric oxide, basically. Okay, so one of these pharmacological agents, believe it or not, is hemoglobin. So let me discuss why hemoglobin is going to block the nitric oxide signaling between the endothelial cells and the smooth muscle cells. Okay, so basically, let me discuss the structure of hemoglobin. Hemoglobin is a protein which consists of 4 polypeptides stuck together. So it's really 4 proteins, if you like, stuck together. Okay, so this is hemoglobin, and it's got 2 beta globin subunits and 2 alpha globin subunits. So it's made up of alpha globin and also beta globin. So these are 2 proteins. Okay, so you make 2 beta globin proteins and 2 alpha globin proteins, form them together in this tetramer. Now, that at the moment is not yet hemoglobin. And what you have to do also is you have to add heme groups onto each one of these globin proteins. Okay, so let me now discuss with you what a heme group is. Okay, so a heme group then is a chemical structure, okay, and it consists of a porphyrin ring with an iron cation coordinated at the center. So let's now look at the structure of it. So I will draw its skeletal structure. So the porphyrin ring consists of these 4 5-membered rings, okay, and each one of these 5-membered rings has 1 nitrogen atom and 4 carbon atoms. So let's draw the other one here. Okay, so here's another 5-membered ring with 4 carbons and 1 nitrogen. Okay, next one down here. Okay, 1 nitrogen, 4 carbons. Okay, and then finally another one down here, I think. Okay, like so. Right, now, that at the moment is not very ring-like, so we're going to have to join it together by carbon atoms. So we're drawing a skeletal structure, remember. So skeletal structures, you don't show carbon atoms. Instead, all of these corners are implicitly meant to be carbon atoms. Okay, so when I draw something like that, that means 1 carbon is connecting to these 2 carbons here. Okay, so we put these carbons in between each one of these rings. Okay, so another one here and another one here. Right, okay, now what we need to do is put in double bonds, basically. So we'll start with this ring up here. So there is a double bond there, then we'll do this ring here. So there's a double bond there and a double bond here. This ring here, there's a double bond there. And finally, this ring here, there's a double bond there and a double bond there. So those are just the double bonds that you need to have in each of these rings. Now, we'll add in the double bonds on these connections. So there's a double bond here and a double bond here. Also, there's a double bond here and a double bond here. Okay, now, what we need to add on now are the little groups that stick off the sides of these rings. So you've got a methyl group coming off here. Then you've got an ethyl group with a double bond here, like so. So these are skeletal structures, so remember this is 1 carbon, and then you've got another carbon here, double bond between the 2, so this final carbon here will have 2 hydrogens off, and this stick here, this means a carbon at the end here, and then implicitly you don't show the hydrogens that come off carbons, so it's just implicitly assumed that the carbon then has its other 3 bonds to hydrogen. Okay, then off this carbon here you have another one of these sort of ethyl groups, so that's supposed to be a double bond there. Here's a double bond. Okay, and another methyl group here. Okay, right, now off these 2 down here, what you then have are methyl groups like here and here, and then you have the same group off both of these 2 down here as well. So you have a carbon, another carbon, and then a carboxylic acid group, which I'll draw out here. Okay, right on the end. And then again here you have the same thing, a carbon, and a carboxylic acid group here. Okay, now that is the porphyrin ring that we have in heme. Now, I want to stress that it is a porphyrin ring. Porphyrin rings are a massive collection of chemical structures, and basically you do not have to have set things in these positions. In heme rings, it is these 4 things that are put in there, but this is an example, basically, of a porphyrin ring. More generally, porphyrin rings are a massive great family, and you can have anything in this position, anything in this position, anything here, and anything here. So this is a porphyrin ring, but it's not the porphyrin ring. Okay, it's the porphyrin ring that you have to have in heme, but it's just an example of a porphyrin ring. Okay, right, so you can't have any other porphyrin ring in heme. Okay, right, so what you'll notice is these 2 nitrogens here don't have enough bonds. So what you now do is in the center here, you put a ferrous cation. So let me just discuss for you a little bit about the cations that iron can form. So iron can form two types of cations. It can form cations which have a double positive charge, a divalent cation, and this is what's known as the ferrous cation. Okay, so ferrous cation. It's also often referred to as iron 2, and you can put a Roman numeral up there, or just iron with brackets, no Roman numeral like that. That all means this ferrous cation. Okay, there's another cation, however, that iron can exist in, which is the iron cation which has a trivalent positive charge. Okay, and this is what's known as the ferric iron cation. Okay, so this is the ferric cation, and it's also sometimes referred to as Fe Roman numerals 3, like that, or again Fe brackets Roman numeral 3, like that. Okay, so basically it is the ferrous cation that you have at the centre of heme, not the ferric cation. And what happens is these two nitrogens form covalent bonds with the iron, with the ferrous cation, and these two nitrogens, they both have lone pairs. So here's a lone pair, here's a lone pair, which are these centres of negative charge, and those centres of negative charge interact favourably with the iron cation and form a sort of electrostatic interaction between the two, which is denoted by this sort of dashed line. Okay, now basically this iron cation, it can actually support 6 what are called coordinate bonds. So if I draw it out, if we draw the iron cation here, it can basically have one coming out above it, one coming out below it, and then it can have 4 in the plane here, like so. Okay, so in a sort of all 90 degrees apart, so this is 90 degrees here, this is 90 degrees here, this is 90 degrees here, this is 90 degrees here. Okay, so basically this heme group, for that's what it is now, once you've put the iron at the centre of this porphyrin ring, it becomes known as a heme group. That's the British English spelling of heme. It's also called H-E-M-E. That's the American English spelling of heme. They're both widely used. Well, probably this one's more widely used now. If you're in England, this one's widely used. Right, okay, so basically this heme group, the iron, the whole heme group is very planar, so effectively it's these 4 bonds that you've got here, they're like these 4 bonds in the plane here. Okay, so this one, this one, this one, this one. So you can form a bond coming out from above, and also a bond going into the page. So there's 2 coordinate bonds still free for this ferrous cation, so it can form more coordinate bonds. It's only got 4 at the moment. Okay, and these 2 free coordinate bonds are going to help you add this heme group onto the sides of proteins, and we'll continue this discussion in the next video.